Okay. Now to start recording. Yeah,
Okay.
it's recording.
Okay.
Okay. Good night. Good night, everybody.
Good evening.
No, right
Good
now
evening.
it's night. So I would like to share something,
Yeah.
and you will notice that the way I share it, it
Yeah.
might also a lot more to the way I look at it as a statistician.
Okay.
From what I shared over the WhatsApp, I was quite ambitious to do several
Yeah.
things. So the one limitation I had was I never wanted to introduce the other packages. So
Okay.
that with R still there is a lot more we could do, hopefully, or at least we can try. Tuko pamoja?
Yes, we are together.
Well, for you now it's different because you probably this is below your scope. I'm more interested in those who are a bit new to R.
Oh yeah.
So maybe as we start, can I know that? Can I confirm that we all have R and R Studio, preferably?
From my side and Steve, we have and our studio.
What about
Yvonne. Yvonne.
I think she's mute or something.
Oh. Yvonne.
Yes, I do. I do have. I use that frequently.
Oh,
good.
That's our. So what I will not want to start with is, of course, the idea of what R is, right? The simple things like, the most basic introduction of R will be things like, 1 + 1 and stuff like that, as you can see on the screen. What I've done, kind of shared the syntax with comments. I hope we all have them. Can I get also a comment that we have them or not? If you have the syntax, please raise your hand. Am I on or off? Okay. John asks, how do you raise your hand like that, John? Well, if you don't, I think it's just shared somewhere here. I have shared the syntax and the data. So let's get started. Well, the first thing, of course, according to the way I shared is, first we would really like to look at the different data types on R, the variable types. I like looking at R in two different ways. First, you need to understand the type of variable, and it is very important because the kind of analysis you'll do eventually is determined by the variable type. For example, the first one, which you can see in the line number 13 where I am right now, we have like the numeric data type, variable type, sorry. Like for instance, the numerals that I've just created, when you look at them, they have they are kind of real numbers. They are continuous numbers. This, of course, is important if you're doing things like histograms to understand the distribution. A lot of numbers follow this system. They are kind of continuous in nature. But sometimes you need to look also at counts. counts which are whole numbers, and R, there is something which I'd like to distinctly point it out here. Like in our classes in statistics, the first descriptive statistics class, when we teach about the different types of data, we only teach two. We teach quantitative and we teach qualitative. Of course, quantitative is any numerical, but the things we know to be categorical, they tend to fall under qualitative in statistics. By definition, of course, statistics is about dealing with things that can be quantified. So most of our analysis focus on quantitative. However, computers split it even further. So we have, like, you know, the numeric variable types, and we have the integer. The main distinction between numeric and characters is numeric variable types, you can perform mathematical operations on them. For example, summation, addition, and summation, multiplication, and stuff. Well, another variable type, the third one, is characters. For example, when you just type letters is like a constant in R, and it gives you all the letters from A to Z. If you type letters in capital, you just get them in capital from A to Z. Notice for numeric variables, we don't have quotes, so I think this one you already know. When it comes to characters, they must always have quotes. It's important that you know, it is important to understand the variables of character, because sometimes there are some character functions which we want to apply on them that won't work with the numeric functions. In other software, instead of calling them characters, they might decide to call them string. In particular, they will call, if it's only one letter or one alphanumeric, it might call it character, but if there are several of them that have been joined together, they'll call them string. The fourth one is the logical. Other software might call them Boolean. Of course, these are true, false. Now, if you consider this, you will notice that the Boolean is a bit different from the character in that, again, it is not quoted. They are especially important for conditional functions. You know, conditional like if, stuff like that, if you want to subset and stuff like that. And the last one is factors. I repeat again what I mentioned earlier. Factors are basically categorical variables, and they can be, of course, ordinal or nominal, depending on the intrinsic ordering that exists. In most cases in R, if you just put any values, it might treat them in fact as factors. Even character values, sometimes even numeric, it may read them as factors and then automatically order them, sort of sort them and give them the labels for the values that they have. So it is important to note that it's when you're reading variables, especially if you're reading data, you want to be careful you don't end up like having everything as factor, because it will really mess up your analysis. Of course, you can label the factors. In SPSS, we will call levels labels in SPSS, but here we just use them as levels. Now, we've just created a factor here in line 47, the one I've just highlighted, and we've just looked at the levels, and when you can see the screen, it shows us the default values to be the levels. Of course, we all understand that you can put the labels that we want, so that when you look at them, you actually see the labels. And this time round, when I run factors, you'll notice it is not showing the initial 1, 2, 3, it is just showing the labels, or rather the levels. Tuko pamoja so far?
Yes, yes.
Yvonne is typing. Oh, I'm happy. Now, since we've all said that we've worked with R, I know we probably understand all that, right? Now, let's look at the distinct data structures in R. I will look at data structures as the different ways we can have objects in R. For example, you can have something like a scalar. You just have like a single value and you store it in an object. I hope you understand objects. Like if I clear my history and my environment, if I just run value 1, it will appear in the history, but it will never appear on the environment. But when I store it in an object A, then I have an object A that has a value 1. It will both show in the history where I've actually run the function to store the data, and it will give me the object that exists there. Now the first distinct data structure I can look at is the vectors. From our own mathematics, we all know, of course, a vector is not a scalar. The only difference between a vector and a scalar is that a vector has multiple dimensions going one way and one dimension on the second way. For example, it can have multiple rows and one column, or you can have one row and multiple columns. Well, you can create a vector in different ways. For example, like we did before with the integer, we know 1 to 10, basically it gives all the digits, whole numbers from 1 up to 10. The alternative way is to concatenate using the C, which gives us the same value. Now, what are vectors according to R? One thing you know about vectors is all of them have, every value in the vector must have the same variable type. Now, if well, there's something good about the vector, isn't that you can almost always extend the vector. For example, here I have the first vector that I created, and I want to concatenate the values 21 up to 25. So when I run it, you can notice that I've extended the vector from 10, I added the values 21 to 25. But there is something important you also want to look at. For example, when you're dealing with the vectors, and this is the issue of coercion. In case you want to put a numeric vector with a character vector, you remember letters are characters. Now vector 1 that we created is numeric. So if you combine them, yes, it will create a vector. However, the coercion will take effect. There are some data types that are stronger than the others. For example, in this case, you can see that characters are stronger than numbers. Let's say you have let's say you have just another vector. You just, like I'm creating right now. I might be having the numbers 1 to 10, and then I want to put true, false. You will notice that in this case, the numeric is more powerful, superior to the logical, in that the logical, they just took the values 1 and 0, 1 to mean true, 0 to mean false. So therefore, going ahead in future, probably you just want to be clear that you don't when you're working with the vectors, you don't force coercion. Or rather, if you're merging, you're clear on what you're doing on that. There is also another important thing which you already know. You can always select a specific value by of the vector. If you know the position of the value you want, you can always easily select it out. For example, we want using vector 3, the value that is indexed at position 15, and we can see that it is an E. Of course, after vectors, the next obvious step is the matrices. The matrix is just the same as a vector. You can look at it as several vectors put together. The only difference is it has, let's say, a certain number of rows and a certain number of columns. You can look at it as being two-dimensional. The similarity it has with vectors is all the values in the matrix must be of the same type. If they are numeric, they are numeric. If they are character, they are character. Or like, for example, we were creating a matrix. We're using the first vector which we created. It has values 1 up to 10. We're going to say we want to have 2 rows and 5 columns. Now, by default, when you just use the matrix vector, I missed you there. Yvonne, is it not clear or?
Thomas, I just felt it is important. Let's say somebody mixes data types in a vector. There is a concept called coercion. So if you put character strings with numerics, R would all convert them into character strings.
Yes.
Yes. So it happens that way, even with logicals. I'll share how it all works out. You can mix, but it will convert them into one data type. I just thought it's important to point it out.
Yeah, thank you.
Yvonne?
Yes.
Yeah, so I think that's why Thomas was emphasizing we have levels of in terms of strength when you're combining, like, let's say, character and a factor, or you're combining a character and logical. So characters are always stronger.
Okay.
So when you're combining, I think when you combine possibly logical and numbers, maybe numerics may tend to be strong. I don't know. We might try, but I know characters are always stronger.
If you combine logicals and numbers, R will convert them into numerics.
Yeah.
That's how it happens.
Okay.
Yes.
Yeah. Thank you.
So thank you for pointing that out. And
okay.
So I just alluded to them on line 79 to 82 as where I've highlighted. Okay. Yeah. So we continue with the matrix. In line 90 now, I'm with the matrix again. So the matrix, automatically it will kind of organize data going downwards, okay, by column. For example, we had our vector from 1 to 10. When we convert it to matrix, you can see that it goes, instead of going by row, it goes by column. Sometimes I've seen somebody who kind of made an assumption and he messed himself up because of that. So in case we want to ensure that the matrix it's kind of aligned by column, then we want to show that, sorry, by row, you want to add this argument that by row it is true. So in this case, our values, as you can see, have gone along the row as opposed to against the row. Like with vectors, you can always subset or get a specific value if you find the index of the position of the column and of the row. For example, the value that is in position row number 2 and column number 2. Oh, I did not create it. Excuse me. We can see that it's value number 7 here. It is row number 2, column number 2. Another cool thing about matrix is you can even add row names and column names using for example, here I'm adding column names using the call names command. And then when I'm subsetting, or rather when I'm extracting the value I want, I can even use the name of the column as opposed to just the position of the column. Tuko pamoja? So the next data structure I want to look at is the data frame. This is especially important because I think most people read in values that are in data frames. Well, the difference between a data frame and a matrix is the fact that the data frame, we have columns that are of different variable types. One could be numeric, another one could be character, another one could be factor. You can still get a specific value using the matrix formula. If you can just index the name of the column and the position in the row, you can still be able to subset that value. Here I've just done a simple illustration. I've created the first vector, the second vector, the third vector. I wanted to show a difference here. To create a data frame, for R to understand it to be a data frame, you need to invoke that it is a data frame you're creating, and then you merge them. So when I look at the class of data, it's a data frame. And further, we can always look at the structure using the str function. So it gives us that the structure tells us, yes, how many observations the entire data frame has, how many variables, or rather the number of columns that exist, and it gives us the difference in the class of variable that each of the column holds. Now, there is another command that people like using, which is cbind, which is to mean column bind, or you can even use row bind. In such a case, if I used cbind on this, what I will eventually have, it's a matrix. This will be a matrix that is around 26 by 3 matrix. And you can see it's a matrix since all the values have been coerced again into character. So it is best that if you're using a data frame, you want to stick to the data frame command so that it maintains the type of the variable that you're using. Of course, since you have a data frame, there are different ways you can look at it. I just mentioned structure, where you can be able to see the type of variables which are important when you're doing your analysis eventually. And of course, you can view with the capital V. You can be able to view without editing. When you use view, and then it opens in a new window. Or you can edit. When you use edit, you can change something and use it. Okay? However, for you to proceed, like right now, it will be hard for me to say list while this one is open. I have to close this editor window for the next function to work. Now, the one which I've called list is another data structure. List is important in that it's an object that can host the other three data structures at the same time. It can host a data frame, it can hold a data frame, it can hold vectors, and still maintain their own type of variable. Here I've created a list where I've merged the data frame which we created and the vector vect2 which we created earlier. So I've created it. If you want to see the list, you can just click on list and it will show you. Now in the first list we have the data frame. In the second list we have the vector that we created. You can notice that the way the lists have been kind of numbered. So for you to subset one of the objects that you've put there, you can just subset using the list function and the value of the object. Or rather, you're using, instead of using one square bracket, use double square brackets and the position of the object. Like in this case, in line 126, we've just called out the vector that was of character. If I want to again select a specific value in that vector, now I use the normal method. After I've already extracted the vector, I again extract the position that I want. So the 7th position we have the letter G. So those are the 4 data structures that I know are commonly in use. And I think I will pause on that again if there is any question before I go to the next bit. If you're okay, you can just say you're okay and then I continue. So your question, Yvonne, is factor a data structure as well? I've seen people look at factor as a data structure, but I will position it to be a variable type, because we can have a vector of factors. You get my point, Yvonne? Yeah. Okay. Before we read that, yeah.
Yes, about the factors, sometimes it's a bit confusing anyway, because when maybe when having it as a data structure and maybe we have this as ordered or unordered. You see, even if we say a character, we will always store it as a character and then convert it later as a variable. And then maybe you want this to be ordered, always ordered when it's accessed. Can we just say it's always when, for example, so I'm looking at a situation where you have ordered, and so normally we find the normal factor, the default is ordered, but I mean the default is unordered. But now we find in some situation where it is it's ordered. I mean, yeah, it's ordinal. Then, so always look at it as a structure. In some sense, as a structure, because when you are reviewing like the big is it the big 5? We have vector. It's always treated as a data structure on its own.
Okay.
Because of the different attributes that it possesses.
Okay. I'm open to ideas like that.
Yeah.
But from where I start.
Yeah.
Well, I understand like a data structure is a way of holding that data, like, you know, Not just
Yes.
the type, but also a way of holding it.
Yes, yes, yes. Yeah, and that's why we find that it always possesses different attributes, like levels of which characters don't have. We have yes, and other labels and all that.
To me, I still find it debatable. I will probably put it far much better under variable because it's a type of variable. Yes, it will definitely have
Yeah,
several steps to create it,
yeah,
whether you want to make it ordinal or nominal. But then I've just, okay, like probably if I Google right now, I will see some people call it a data
yeah,
structure.
yeah,
But from my basic understanding and also from at least some time back when I've
yeah,
actually done some courses,
yeah,
I actually kind of felt it suit best as an
yeah.
instance as a variable type.
Oh yeah,
And
sure.
let me also mention this.
Yeah,
Again, you see in statistics, when like here when we teach statistics, we consider factors or other categorical variables as qualitative data. Okay? Hello, Nanpata? John?
yes, Nakpata.
Now, in statistics, we focus on the numerics. We focus on numbers and integers. Okay? And
Yes.
then other categorical, we don't, we call them qualitative. So whether it is text, factor, or all other things. But then, most statistical software, they actually felt, they've been using categorical variables, also not so much as a qualitative one, but as something you can use also quantitative. So that's why I will still put it more on variable, but like Yvonne has put it, I think it depends. It depends, but then I think this one will be arguable. Yes, we need to argue over it over some coffee sometime till we get a good definition, classification rather for it. Happy? Okay. Can I proceed, please? And thanks for the contributions on that. Aye. Okay. I put this third part on randomizing data because like in my classes, I don't always get the data. And there's the beauty of randomizing data is that you get complete data sets when you're running with the student. And there is one downside of randomizing data in that I've not seen a function that just randomizes whole numbers, like integer values. So if you want to randomize integer values, probably you just do the usual randomizing steps and then convert them to integers. Well, we all know the first one is to randomize using normal distribution. Of course, the arguments are you need to put how many random numbers do you want. You want the mean and the standard deviation. So in case, let's say, I want a value between 1 and 100, then I will put my mean to be 50, standard deviation to be 15. There I'm using the rule of thumb that, all the 99% of the values should be within 3 standard deviations. So 3 standard deviations there is 45. So 50 plus 45 is 95, 50 minus 45 is 5. So if I want a value between 1 and 100, that's what I will usually do. Of course, it is random because as you can see when I randomize again, everything is random. And I can also randomize using uniform distribution. The difference between normal distribution is that we have a bell shape that is symmetric with most of the occurrences somewhere between somewhere near the mean. Uniform, the The arguments include you put the minimum value, and it will never give you a value less than 10 in our case, and it will not give me any value greater than 100. However, all the values have equal opportunities. Any value between 10 and 100 have equal opportunities of being selected. So if I do that, well, you can see that. And of course, the last one is exponential. You can just put the value of n and then you just randomize between 0 and 1 exponentially. So notice, actually there are more than one. And of course, in a class setting, I will definitely ask the students to set seed. The set seed command, I think we all understand, helps us to have the same starting point for randomization. That will mean that when you do the randomization, all of us will get the value. Notice, originally, I had run and I got these two values, 42 and 51. And right now, I've just run them, I've gotten the same values. Now here, I'm just doing a histogram so that you understand the difference in the distributions. The normal, now I'm randomizing with n equals 2000, that is 2000 values. As you can see, the distribution tends to be normal. It is symmetric about the mean of 50. Then the uniform, notice, almost every value between 10 and 100 have equal chance. So if it is so big, probably this will appear as if it's a straight line at the top. And of course, the exponential, as you would expect in our case, it's kind of decreasing exponentially. So you want to randomize looking at which distribution do you want. I think that you can even randomize using other distributions. Like you can see here, you can randomize using gamma, and of course the number of random variables you want, the shape you want, the rate, scale, and all those things. That's the beautiful thing about R. You can randomize using any distribution you want. But for now, we're not going to use random numbers. I felt it would be more interesting if we go to our own data set. I'm hoping that we all got the data set that I shared out. Did we? Okay. I like always setting my working folder. I like setting my working folder. Because it makes my work easier when I'm reading in data. Right now, if I check what is my folder, I can clearly see that my folder currently is the documents folder. That's the path. But I want to set such that this folder where I've put the data to be the one where I want to use. So for you guys to access the data easily, you may as well also set the working directory, which I know you know how to. There is something else I like about when I have my working folder, I can easily check what are the things, the items that are there. It will give me the list.files. I like using it because it gives me not just the name, but also the extension. Like I can see here, there is something that is a PDF. I don't think you have it, but most of them here, they are CSV. CSV is separated variables. So it means I understand what lines to use. Now I want to read this one that is called population estimates.csv. Let me open it from here. I wish I had opened it earlier. There are many ways you can read data into R. One of the most common ones I've seen is read lines. Now, read lines, we all what we know is that it will read every line as a row. It is useful in some cases, especially if you're working with unstructured data. Then I would probably use the read lines. In our case, however, we have CSV value data, and this data, when you look at it, that's how it looks like. So let's just read it using the first command. So I've just let it as default. When I view it, you can see it's read almost as if it was reading using read lines. It's kind of combined all the columns into one, because I left out several arguments. The first one is the fact that the first two rows are actually not data rows. They are kind of metadata. So I needed to have started at the third row and then it read everything. Now, please take note that in case you have a full column that is blank in between, let's say, like you can see here, this column I have just made it to be blank. And if you have a full row that is blank, so that row and this column are blank. Most software, not just R, but most statistical software, they will read up to where there is a complete row that is blank or a complete row column that is blank. So it will read anything between A1 up to H22. But we don't want that for now. Luckily, I've not saved it. So I'm going to read it again, but this time round, I'm going to add some of those arguments. Like, for example, I want it to read, you can see the variable names are on line number 3. You can see they are ridiculously big variable names, which I don't like. I prefer them just being small. So I'm going to say header is true so that it reads the variable names in that line. A long time ago, I remember people were just using CSV. I don't know how it kind of died out its popularity. Nowadays, CSV2 is the one that is being used a lot. But with CSV2, you need to indicate, even if you're reading .csv, you need to indicate that the separator is a comma. And then I've said skip the first two rows. There is something else I've added. Actually, I've gone a little bit ahead of me. This is where I did the first one. So when I read it in, it reads properly. When I look at the variables, well, remember str is to look at the structure. Something has happened. Every character variable has been read in as a factor, which I think it's in a lot of times has been the case. I've kind of seen it in many instances. There is a limitation by doing it like that. If, for example, you can see that the estimate base 2010, its factors, and it has 1006, okay, 1006. Already in Excel here, because there are these commas, that's strange. Okay. Are read in the commas. And because of the commas, they are converted to character. And because of that, they are now, how do I put it? They are factors. They have been read in as factors. Now you have a problem with that. And those factors are there are 3,208 levels. So that means this value 1006 has actually been read in as a value 1. This value 1017 has been read in as value 2. So people need to be careful when you're reading it in, especially if you, if you're going to use it for analysis. So there is this other argument you can add, which means don't read in strings as factors. I've put it as false to say don't read in string as factors. So when I run it this time round and I look at the structure, you will notice that the character variables have been read in as characters. So something you'll notice, I've created a new object called population data, or rather pop data. This object, its type is a data frame, and it has the data that we have. Any questions so far?
I have a question.
Yep.
Hello, Gama. Yeah, my question is, what is the advantage of read CSV2 over read.csv like by itself? Because like I understand it sounds like an upgrade, but then you realize that the read.csv is still there. So what are the advantages over the other? Because what you did here, I think read.csv by itself it still can do the same.
I think what took me to CSV2 was, I think, a difference in R. Because I tried once with using CSV and it failed with that R version.
Okay.
And then so I went to 2 and then I stuck to 2. And I've never gone back to CSV, but I can't say that one is better than the other one over something.
Okay.
Yeah, it was just an R version.
Because for me, I've always been using the CSV, so yes.
Okay, thanks.
Thanks.
Okay, so we have our data. Well, there is a lot to do with data management. Just but to mention but a few. Of course, one of them is you need to look for if there are oddities in the data. Of course, you can look at oddities through summarizing, also through plotting. I will not look at oddities using plotting in our case. I'll use a bit of summarizing. And another aspect of management, if there is an entry that can be rectified, you want to rectify it. Another important aspect of data management is providing the variables or rather the values that are needed. And in our terminologies, let me use the term subsetting. And then there is another thing which might be useful, but in our case, we won't do a lot with it. And that's set goals. When I gave you guys the structure of population data, there was 117 variables. That is insanely too many variables for me right now for this simple exercise. So I'm going to select a few. I studied so that again I can get the census, population estimate, births and deaths, just from this data set. And their index positions are, of course, I was taking also the state, the area name, sorry, no, not the area name, the state, the census, in that population estimate, births and deaths. And their positions are in column number are actually indexed 2, 9, 17, like that. So in my case here, I'm going to subset. Of course, to subset, if it's a data frame, use the square brackets. And if you want to put all the rows, you leave the part for the rows to be blank, and then you subset the columns that you want. And you will know that you can rename we can rename the cost to Sisla. So now if I check, see that, hello, am I clear now? The same for population estimates, but for births and deaths, they are kind of complete. So you'll notice that I will basically focus on the births and deaths. Oh, there is something I need to show you here. Now, when I tried kind of to convert this to numeric, and that's when I noticed there was that error. When I tried to convert the census to numeric, something happened. Only the values that were below 1,000 were included because they did not have the commas. Okay, so in our case, we will not need to convert them for now. We'll just leave them the way they are. But before you convert them, probably you will want to find the comma inside each and every value, and then replace it with a blank. Okay, I think the function is usually g substring, right? There's a function like that, g sub or g substring, and then you can be able to replace the no, not g sub. I think there is sub find. I'm not so sure, but I think it's one of the string functions. Okay, so we want to look at oddities in yeah, I thought it was g sub. Thank you, John. We want to look for oddities, and of course I'll start by looking through the mean. When I run the mean, I can see that it doesn't give me the correct value. It doesn't give me any mean because there are several values that are not available, or rather not applicable. Of course, I can use the function for mean when I exclude the NA values to get them, but it doesn't really help me to know how many values are actually NAs. So if I run the summary, I like using it. It will kind of tell me, like here, for the births, I have 78 values that are not applicable, and for the deaths, I have 78 values that are not applicable. Okay? The good thing is, now what I want to do rather is, I would like to do some small analysis on them, but I don't want this NA. So I'm going to, since I don't have a reason, or rather I don't have information to help me know whether they are NAs or not, so I can't edit them. So I'm going to actually remove them. I'm going to remove them. Like right now, you can see that I have 3,273 values. I'm going to check how many births have actual values as opposed to NA. And also at the same time, I want those rows that have births to also have deaths. I'm going to create a logical variable here, and I'm going to use that logical to help me subset the rows, because this logical variable has 3,273 has a length of 3,273. So it's going to help me subset such that if now I look at the number of rows, I've actually reduced this by the 78. It's as if the ones that had NA values in deaths are the same ones that had NA values in births. Now, if I do my summary, you can notice that this time round, it only reaches at max. It doesn't give me the NA value, so I'm good to go with my small analysis. But there is something I picked up. For example, here the births are 0 and the maximum value is 999, yet the third quarter is 142. Well, it raises questions. Could this 999 be an outlier? There are many ways you can look at it. One of them, of course, is to scroll through the variables themselves, or you can just use the sort function. I'm going to sort decreasing so that I can see how it's going. So I can see there is 9999, several, and 700s and 600s. So they are not really outlier values, or rather it's not one value that is just out of the ordinary. So I'm going to leave the value 999 to remain as that one. Same also when I look at zeros, it's not from nowhere. There are zeros, ones. What is still strange is they're actually, I can see 1.021. So I think the births were in some sort of thousand maybe. Same thing can apply with deaths. When I look at it, again, there is the 900, it's kind of slowly reducing to 300s to 200s. So we don't really have outlier values that are by themselves outliers, so that we can maybe exclude them. Even in when I put them in increasing, it's from 0. There are several 0 deaths. It starts with 1 and stuff. Yep. And it continues. Again, you will notice that there are some values that are a bit strange, like, you know, the number of bars 2.1. It could be maybe there were some entry errors or something. We don't know for now. So I'll just leave them the way they are. Now that we can say that our data, at least the two that I want to use, are a bit clean. So I'm going to go ahead and let's do some analysis. Of course, the simplest one are descriptive analysis. Of course, we already know the summary. You can summarize for the entire data frame, or you can summarize for the individual ones. If you not use that one, you can still use the simple finding the max. If the NAs are there, you might want to add the argument that you want to exclude the NA values. What I like about R is also it can give you the position of a specific value that you want. For example, the maximum value, we know that is in position 347. This is the first position that has 999. Okay, so in case you have multiple, I'm not so sure how to go about that one. The same with if I want the position with the minimum value, I can see the very first position with the minimum value was the position 279 in that data frame. Well, you can always do other small analysis. For example, if I want to look at how many values are above the mean, I've done something funny here. I've calculated the mean, okay, of the births, and then I'm just getting how many births are above the mean. Okay, I'm finding the length. Probably there could be some simpler command through a package or base that I'm not so sure of. But in my case, I can see that there were around 898 values that were above the mean. You can use all this to do a lot, you know, R, you can use it to do a lot of, well, to answer several questions. Of course, the other part of analysis apart from description is finding relationships. For example, I want to find, is there some correlation between the populations that had deaths, the number of deaths and the number of births in the different populations? Well, when I just use the correlation function, just the core, it gives me the correlation coefficient rho. Now rho, by interpretation, values between 0.3 and 0.7 are considered to be moderately strong, while values that are above 0.7 are considered to be strong, and values below 0.3 are considered to be weak. I'm talking of absolute values. If it is negative, it means there is an inverse relationship. In our case, we have a moderately strong relationship between the number of births and the number of deaths in the different populations. That means the population that had high births kind of tend to have higher deaths. Okay. However, with statisticians, you won't use this one just and let it go at that. You might want also to do a test. So when you use the correlation test function, it does the Pearson's product moment correlation. Well, Pearson is kind of, we call them parametric tests, okay? And when you, of course, by interpretation, you look, many people look at the p-value if it is less than 0.05. In our case, it is far much less than 0.05. And it means that indeed the correlation is not equal to 0. It gives you a confidence interval. You can see that the value 0 is not in that confidence interval. Okay, so yeah, there is some strong, the correlation is moderately strong and is statistically significant. And of course, we can also do linear models. Well, in a big way, correlation and linear models are very much related. Like I think rho is the slope coefficient also in linear models. Of course, there is the linear model function, LM function in R, and then you want to say, in our case, I'm putting births to be independent, but deaths to be the ones that depend on birth, and of course, I put the data. So when I find the function, the model, it gives me the intercept as 46 and the birth as 0.5. That means for every 1 increase in birth, there are 0.5 increase in deaths. If of course you want, in many cases, we don't want to just use this result as the way it is. What you want to do is to actually do the test itself also. So the summary function helps us also do the test. I can see that the intercept is significant. The births are also statistically significant. And of course, the model explains just 33% of total variability, and the model itself is statistically significant. Okay, so yeah, there is a lot of relationship between births and deaths in that data. Of course, I can also plot. When you see the plot, these are just probably some outlier values in deaths. Also, it's strange. In these populations, there are no births, but there are several deaths. But you can see clearly that there is like a linear trend with the data. So I'm going to add that line. You can see it's a linear trend. The slope of the line, we already know the slope is 0.53 and is positive. So let me pause there in case somebody has something to add.
I think the explanation is a bit clear, and I think on our side we are okay.
Okay. So far, everybody seems to be good. So then there's the next bit. This one is not relationship, but sometimes in many cases people want to compare different means. Okay. Just to be clear, do we have, how long do we have? It's right now 8:26. Do I try to push up to 8:45?
8:45, yeah.
Okay, thanks.
Yeah.
So, well, to compare means, people probably know the two main ones. That is, the first one is t-test. This one is when you have two groups and you want to compare the means between the two groups. So I'm going to create a new variable called new var, and I'm going to make it to be factor. And then I'm going to compare, well, I just kind of randomly allocated people into the rows into the two groups. And then I'm going to compare the births and the deaths, sorry, the births over the two groups using a t-test. Well, it doesn't make sense in this case, but please bear with me. The only reason I'm using birth is because it's a numeric variable, okay? Well, when you can see, the p-value already shows that it's not statistically significant. The mean in the first group is 123. The mean in the second group is 127. Let me just show you again how I did the group, okay? So I just created this new variable, and I was just including and excluding like that, okay, till the end. Kind of not random, just in that alternative fashion, okay? Another way of comparing is using what we call the analysis of variance. The analysis of variance is just a slight modification of t-test, if I might say that, because you use it when you have more than two groups and you want to compare them. So I'm going to create another variable. This variable I've just created another variable of 4 groups, and then I've just allocated all of them into the 4 groups, okay? Now, I'm going to use that second variable, the one that has 4 groups. I'm going to do an analysis of variance. The analysis of variance itself shows that, well, of course, the degrees of freedom is always the number of groups with -1, okay? And for the residuals, of course, it's the total degrees of freedom minus this one. In our case, you remember that we have 3195 rows, okay? So when you do 3195, of course, the total degrees of freedom, you subtract 1. It becomes 3194. 3194, when I subtract 3, then it gives me 3191. This is the residual degrees of freedom. And of course, there is the sum of squares. I don't have the formula right now, but it's just basically the variance excluding the divisor of n-1, okay? That's the sum of squares. When you do the summary of it, so of course, the summary gives you the better look at the analysis. This is kind of the analysis of variance table we've all been trained to use, where you have the degrees of freedom, sum of squares, which are just the same as the ones up there. The mean sum of squares, of course, is the sum of squares you divide by the degrees of freedom, and then the f value, which is calculated, and then the p value here. In our case, the p value is greater than 0.05, meaning, well, the groups are not so different, okay? And I understand why, because the way I just I kind of, I wouldn't have expected anything different. If I want to get the coefficients for the different groups, now the intercept, it's the mean number of deaths for the first group. Now the value for the second group is not 5. It's actually, this 5 is the difference between the second and the first group. So basically, it's claiming that the second group has 5 groups slightly more than 120. So it's around 120 point something, 125 point something. The third group compares also to the first group. That means the third group is around 7 deaths more. That is 127 deaths on average. And the fourth group had around 8 deaths more, which is around 128 deaths. And of course, if you want to have a look at, well, I know many people in agriculture kind of like comparing the different groups. Now notice this Tukey HSD helps one to compare the different groups. Like you see, it compares group 1 and group 2. What is the difference in the mean? It is 5. Okay, as you can see, this is the 5 that is here. The lower interval is -16. The upper interval is 27. As you can see, 0 is contained between the lower and the upper interval. So it is not surprising that the p-value is greater than 0.05. Notice group 3 compared to group 1 is 7, as you can see here. With the, of course, the intervals have 0 in them, so we don't expect them to be I don't expect them to be statistically significant. Also, group 4 compared to group 1, it is 8, as you can see here. And they have, the intervals have, they have 0 in them. When you compare now group 3 and group 2, you can see again is the same thing. So many people who have seen, especially in agricultural research, they like using the LSB. And I think this function, Tukey HSD, helps us to be able to answer this question that they have, where they like comparing the different groups like that. Personally, I would have just been okay understanding it here and here. I would have just been okay, but some of people would prefer having this, these lower and upper intervals and for the different groups compared. Tuko pamoja hadi hapo?
Yes.
Yes.
Happy? Okay. So I also mentioned graphics in R. So the main thing I wanted to do the graphics is I wanted to share out the fact that what I really like about R is the fact that you can have multiple plots on the same graph. This is a bit different with other software. For example, let me create, I'm creating this vector called means, okay? As you can see, means has the averages for the different groups. And please notice something. I used a loop, okay, to get the averages for these different ones. The reason I did that is when I looked at the groups, at the average here, the first one was 120, right? And the second one was 120 plus 5, as you can see. The third one was 120 plus 7. The fourth one was 120 plus 8. Okay? And not so sure which function in the base R can do that one, can just give us the means for the different groups like that. So for me, I just did a quick for loop, and then I calculated it. And then now I wanted to now plot. You remember we had our plot for the linear regression, and we could actually add even the plot for the ANOVAs, you can see, and they are all on the same plot. So this is something I really like with R. There are a little bit more things we could do apart from just this. This is just a base introduction, but one thing I like about this is if you have multiple, let's say, linear models, you can put them on the same graph and adjust their axis, label them appropriately, and help you discuss the different linear models that you have. That is something I really like, and I find it very cool, even from the base R. And that would be the small bit about the plot. And then functions. Now, probably this is my last one. Now functions, sometimes in R, the beauty of R is you can write a function to do something that you want to do. Here I want to demonstrate the, what do we call this? Central limit theorem. So central limit theorem states that if I have data from any distribution, if I randomly select them and I take the mean of the samples, and then I take so many means of so many samples, then the distribution of the sample, of the means of those samples, will tend to be normal. So I'm going to try and show it here using this function. So I've just called it CLT fun, as in CLT function. So the function will have will take a value n. So the n will be how many times do you want to sample, okay? And it will take a value x, that is what is the size of the sample that you want, and then a value dist, which is which distribution do you want in your which distribution do you want the base data to have, okay? So I've just limited it to normal, uniform, and exponential. So if you type normal, it will run the first one, the main data to be normal. If you say uniform, it will run it to be uniform. And if you say, if you don't put anything, it will just take it to be exponential. And then I'm going to, now the second part is to get the means. I will sample the first time up to n times. And every time I sample, I take the mean value and I store it in a vector called means. So if in my case here, the default is 1,000, so it will be going to the data which has been created data 1 and take the first sample, get the mean, store it as mean in the first position, go again the second time, the third time, up to the 1,000th time. And then the last part is I want to just create the histogram of the means. So when I run this, let me demonstrate it. So I'm saying I want to do like, I want to run, to collect 10 samples of 30 that are following normal distribution, and then I want to plot their means. This is what I want to do. You'll notice that their means are not really normal, okay? If I put 100, tends to be normal. If I put 1,000, even more, tends to be normal. If I put 10,000 times, becomes even more normal. So if I change this one to become uniform, still it is normal. If I put that I only want it to be 10 times, we can see it's not really normal. If I take samples of 100 each, still it's not normal. But if I put, the more I collect, the more it tends to be normal. Well, the reason I put this bit of function is because sometimes you may just, you might be like looking for even help online and you don't get it and you know what you want to do, so you can quickly write your own function. However, many people have done several things and they've worked on packages. Honestly, I was not sure I was going to reach here. So I also told you guys not download any package. And so I just wanted to mention that, you see, all these things, probably there is a package that can do this. Okay? Like for example, I would like to look at here where I calculated the means here using a for loop. I know the package player has it has a function called aggregate, which can do that very easily. It can give me the means for these different groups very easily. So the packages help us in the part. Oh, there is also a par package. Well, there are several, I think. Yeah, there are packages that can help our work easier. make it easier. And I think that will be now the end of my lecture. Is it a lecture? Of my presentation. I'm just 3 minutes from 45, from 8:45. Thank you so much for being attentive and for your cooperation. Yeah.
Oh, great.
Open to
Thomas,
suggestions. Yes.
Can you also T-apply? T-apply, can this also work for that case?
But I think T-apply works with the player.
Sorry?
So T-apply works with the player package or the player package, right? Not on the base R.
It's on base R.
Okay, I thought it was in player. Sorry, my bad on that.
Oh yeah, so or you can also do buy or something. We have also buy in the base, yeah.
I think buy works with aggregate function.
They can also work independently.
So they can also work independently. For that case, yeah. Yeah.
Yeah. Yeah. I'm looking up for the nice comments.
Yeah, sure. Okay, for my side, I think it's a very great presentation. Maybe you can hear from the team.
Yeah, thanks a lot. Yeah, it was well presented. I like the way you aligned everything. Lots to revise and even learn more. Thanks.
Thanks a lot. It's nice sharing with you guys.
Yeah.
And I think we'll be giving you more statistical units too.
Sure. You're doing it well.
Yeah, we'll be giving you more statistical units. Yeah, I think it's well conversant.
Mm-hmm.
I'll be trying my best.
Yeah, thanks. Okay, maybe Yvonne, Tony is just joined now.
Yeah, I kind of noticed.
Yeah. Yvonne.
Yes, John. That was a great presentation.
Thank you.
Yeah, that was really nice.
Thanks a lot. And also thanks for the nice comments.
Oh, welcome. So, Edward.
Nalo. Hi, John.
Hi.
I've been digesting the presentation. It was awesome.
Thank you so much, man.
Yeah.
Tony, you know, you joined class when the teacher has already started. Tony.
Hi, John.
Hey.
Hi.
Sorry, I came in late, but I think it was for the part I got you. I think it was a nice presentation, and maybe if we could share the script with us.
Yeah,
I think
I'd
it would
share
be
it, but let me share it again.
Yeah, sure. We'll appreciate.
Share it again because I think there are some small edits.
Sure. We'll appreciate.
Thanks.
From now henceforth, I think I'll start uploading the videos. We already have two.
So I need to stop recording.
So this one, you can stop recording now, I think. So we will share